This is a heat diffusion simulation I built in Python. Every peak and valley represent the temperature at a point in space, evolving over time according to the heat equation. Here is another view of it. And this is the same idea, just in one dimension. In this video, I walk you through the heat equation, explain its solution, and share the code I used to build it. This is the one-dimensional heat equation. It is used to describe, for example, the temperature distribution along a rod. Here, U represents the temperature, the variable x tells us where we are along the rod, and T represents time. So this equation describes how the temperature changes at every position as time passes. This constant, alpha, is called the thermal diffusivity of the material. It determines how quickly heat spreads. We're not using ordinary derivatives, written in d, we're using partial derivatives, written with this symbol. This is because temperature depends on two variables, space and time. So the left side tells us how temperature changes with time. But the right side is more interesting. It contains the second derivative with respect to space. Why the second derivative? Because the second derivative measures curvature. If the temperature at a point is higher than its neighboring points, the temperature profile bends downward, so the curvature is negative, this value is negative, and the heat equation predicts that temperature at that point will decrease over time. On the other hand, if a point is colder than its surrounding points, the temperature profile bends upward, so the curvature is positive and this value is positive, so the temperature at that point increases. In other words, the second derivative tells us how a point compares to its neighboring. And that is exactly what heat diffusion does. Heat flows from hotter regions to colder regions until the temperature becomes uniform. But knowing the equation is not enough, because we need to solve it. And to solve it, we must know what the system looks like when it started. This is called the initial condition. We also need to know what happens at a specific point, example at the ends of the rod at every time. This is described as the boundary conditions. So our problem consists of three ingredients: the governing equation, the initial condition. It is an initial condition, let's suppose here it's a combination of sine waves, and the boundary condition, let's suppose here it is 0 at the ends of the rod. So how do we solve this issue so we can obtain a clean solution that describes the temperature over time and space? One elegant approach is called the separation of variables. In this method, we assume that the solution can be written as a product of two functions. One depends only on space and the other only on time. I'm not going to go through the algebra in this video. Instead, let's jump to the result. This is the analytical solution for this particular problem. The sine functions describe the initial spatial distribution of the temperature, and the exponential terms describe how the system evolves over time. Notice that the exponential always decays. This means that every temperature difference gradually disappears, which is exactly what we expect physically. To make it easier to visualize, let's plot these functions. So here's Desmos graphing tool, a great graphing tool I always use to plot functions. The first two equations here are our initial conditions. So this is the sine pi of x, and this is the half sine 3 pi of x. This is the decaying function we noticed for the first term, and here is the decaying function for the other part of the initial condition. Here's the combination, which is the final response of the system. Here, y is actually the time domain. The y direction is the time domain, and the x direction is the dimension, because it's one-dimensional problem, and the z represent the temperature. So we can see initially here is the distribution of heat over the x-axis when the time is 0, and over time it decays like this according to the decaying function. And the diffusivity factor, which is a here, presented in the exponent part here, it determines how faster the heat will decay. So if we increase it, you can notice that it decays faster. If we decrease it, you can notice it gets slower, and like this. So yeah, here is the general solution. Here's the plot of the general solution. That is the initial condition of the heat, and it decays over time. Really intuitive. So far, we've been describing heat flow along a one-dimensional rod, but most real-world problems are one-dimensional. Heat may spread across a surface, for example, or throughout a three-dimensional object. So let's take the next step. The two-dimensional heat equation looks very similar to the one-dimensional version. The only difference is that the temperature now depends on two spatial variables instead of one. Instead of only x, we now have x and y. So our temperature becomes a function of three variables: position in x, position in y, and time. Something else has changed. Instead of writing second derivative with respect to x, we now write this symbol. The Laplacian. It simply combines the curvature in both spatial directions. The first term measures the curvature along the x, and the second one measures the curvature along the y. When we add them together, we obtain the total spatial curvature across the surface. So the physics hasn't changed. We're still asking exactly the same question. How different is the temperature at this point compared to its neighborhood? The only difference is that each point now has neighbors in two directions instead of one. So how do we solve this equation? Just like before, we use a separation of variables, but now our solution depends on three independent variables. So instead of separating the solution into two functions, we're going to separate it into three. One describes how temperature changes along the x direction, another describes the y direction, and the last one describes how the solution evolves over time. I'm going to skip the derivation again, and instead, let's look at the analytical solution. So this is the general solution for the problem. When I say general solution, I mean before specifying the specific initial and boundary condition we did with the one-dimensional problem. So after specifying them, the summation will collapse and we will wind up with a specific solution. We still have the exponential decay, we still have the sine functions that describe the spatial distribution. The only difference is that we now have sine function of x and for y. So let's implement this solution in Python. Every frame of this animation is computed directly from the analytical solution we just discussed. The colors show the temperature distribution across the plate, and if we view the same data as a surface, the height represents the temperature at each point. And that's the heat equation. Starting from a single differential equation, we built an analytical solution, visualized it, and finally turned it into a Python simulation. I hope this video made the equation a little less intimidating and maybe even a little beautiful. If you'd like me to share the Python code for these simulations, let me know in the comments. If enough people are interested, I'll upload the full project. And if you'd like to see more videos on mathematical modeling, simulation, and computational engineering, consider subscribing. Thanks for watching, and I'll see you in the next video.